Okay, welcome back. I missed you guys last Thursday. I was on an NSF panel, so we can have a makeup lecture at the end of the semester, or we can devote that time to your presentations. Maybe that's what we'll do. Speaking of which, you should be thinking carefully about your course projects. Remember, they have to be 20-minute presentations here on Zoom, and that's the extent of it. So you should be thinking carefully about that. And I'd appreciate it if you'd let me know, say within 2 weeks, what you're going to do for your course projects, so that we can ensure that we have a roughly equal level of engagement among all of you. So sometime during office hours in the next 2 weeks, contact me about that. Okay, we're talking previously about the plane strain problem for rigid, perfectly plastic materials. There's a simpler and also interesting problem which relates to your current homework, and that's called the anti-plane shear problem. Anti-plane shear means the direction of the velocity is orthogonal to the plane, say, of the screen, but it depends only on the coordinates in the plane of the screen. So for example, in anti-plane shear, a velocity field would look like this. A single component, W, let's say, in the direction of K, which is perpendicular to the page, so it's E3. And that W only depends on X1 and X2, the coordinates in the plane of the screen. So we'd like to see if we can construct a stress field, assuming, again, a rigid, perfectly plastic material. Construct an associated stress field in equilibrium, for example, from this velocity field. So the first order of business is to compute the spatial velocity gradient. To do that, we use the chain rule as usual, so we can write ultimately dv is L operating on d small x. And to extract L, we simply use the chain rule, right? dv is dwk, k is fixed. dw is the gradient of w dot dx, so this grad is the spatial gradient in the current configuration. And here we immediately identify a tensor product of two vectors, that tensor then operating on dx, gradient w here, because w depends on the in-plane coordinates, say Cartesians. In a Cartesian system, we'd write that as w comma alpha e alpha, alpha sums from 1 to 2. So immediately then, we deduce that the spatial velocity gradient is k tensor product gradient w. We need its symmetric part in the flow rule, the rate of deformation tensor, a half k tensor product w grad w plus grad w tensor product k. Here's the flow rule again for the rigid, perfectly plastic material. Still we're in the domain of isotropy. Towards the end of the course, we'll revisit this and talk about crystal symmetry. By comparing this equation to this structure of D, we deduce that tau, the deviatoric stress, must have this structure, some vector, I'll call it tau hat, tensor product k plus k tensor product tau hat, where then lambda times this tau hat must be 1/2 gradient w. So you can regard this as the reduced flow rule for the anti-plane problem. Tau hat is a stress vector, essentially, that contains the transverse shear stresses. Okay. And this is, however, an entirely in-plane vector. It's a vector in the plane of the page. Okay, let's look at the yield criterion, the von Mises yield criterion, excuse me, which says that you have yield when the squared norm of the deviatoric Cauchy stress is twice k squared, where k is the yield stress in shear. And if you But look at the squared norm of this tensor here. That's just tau inner product with itself. I'll let you do that. Take the inner product of this with itself. You just get, because k is a unit vector, you get 2 times the vector product of tau hat with itself. And then this criterion says that you have yield when the norm of tau hat is equal to k. So you can think of tau hat as containing the shear stresses, which would be, say, T31 and T32. So tau hat is the vector T31 E1 plus T32 E2. Okay. From this equation here, if we take the norm of this equation, this anti-plane flow rule, and require, as you recall, that lambda should be non-negative to ensure dissipation, we get, using the norm of tau hat as k, we just get lambda is 1 over 2k norm of grad w. Put that back in here, and we get tau hat is k times a unit vector, call it t, where t is the normalized gradient of w, in other words, grad w divided by its norm. And since that's a unit vector now in the plane, we can associate it with an angle theta, cos theta E1 plus sine theta E2, like this. And this notation then is essentially the same as we discussed in the case of plane strain, where we had a similar t vector, in fact, defined in exactly the same way in terms of an angle theta. So theta depends on x1 and x2 because of this definition of t. Okay, so if we put everything together into the Cauchy stress, that's the pressure part and the deviatoric part. The deviatoric part now, with this formula for tau hat, remember k is the yield stress and shear, it becomes this, k t tensor product k plus k tensor product t. That's very similar to what we had for the plane strain case, except instead of, in place of the fixed vector k, we had s, the orthogonal vector of t in the plane. Okay, so the structure is similar, but actually simpler. For equilibrium, let's say without body force, we'd want to ensure that the divergence of the Cauchy stress, spatial divergence, is 0. That implies with this formula that gradient P is balanced by K times the divergence of the right-hand side. And some time ago, we had a formula for the divergence of a tensor, which is itself the tensor product of 2 vectors. If you apply that here, you'll get this second line. And this term here, grad T on K, that's just the derivative of T in the direction of K, in other words, the 3 derivative. But T doesn't depend on x3. So that directional derivative would be 0. And we just get the equation then to solve, assuming perfect plasticity, so K is a constant, bring the K to the other side and sneak it inside the gradient. You get grad P over K is div T along K. That tells us a fair bit of information already. It tells us, for example, if you write gradient P in Cartesians, then this would say that the in plane components of the gradient, P comma 1 and P comma 2 are 0 because there's nothing to balance those on the right-hand side. Whereas P comma 3 would be K times divergence T, right? Because K is E3. So this first pair of equations tells us that P is some function of x3 alone, call it capital P of x3. The comma 3 of that then is the ordinary derivative of capital P, and that has to balance K div T. We take a further x3 derivative of this, that tells us that capital P is a linear function of x3. So there's some constant c times x3 plus another constant. And c then has the interpretation of an axial pressure gradient, that is a pressure gradient in the direction of k. So the equation we solve is C equals K div T, where C has to now be a constant axial pressure gradient. Constant because of equilibrium. That's what we deduced from equilibrium. So because T is determined by this angle theta, this is one equation for the angle theta, scalar equation to determine theta. Once you know theta, you know the shear stress vector, which then tells you the deviatoric stress. Okay. So you reduce it down to a single equation. Remember, we had two equations in the case of plane strain, so this is substantially simpler. Well, in your homework, you have something like this, except I've asked you to look at the case of zero axial pressure gradient. So let's examine the case of a zero axial pressure gradient, which means no pressure gradients along the z direction, the x3 direction. So C is 0 in that case. And we simply solve this simple divergence equation where T is a unit vector. Let's see what this implies for the angle theta. T is determined by theta. Well, we can use the chain rule to write, for example, dt is grad T, the tensor grad T operating on dx. If you recall the plane strain discussion, dt was s d theta, where s is k cross t. It's the vector orthogonal to t lying in the plane, same plane as t. And then d theta, of course, is grad theta dot dx, so we can extract the tensor product here operating on dx. Okay, s, by the way, is just minus sine theta e1 plus cos theta e2. This tells us that grad t is s tensor product grad theta, and the divergence then, which is by definition the trace of the gradient, the trace converts the tensor product to a dot product. That has to be 0, so we just conclude that s dot grad theta is 0, which means that theta has no derivative along the s trajectories. We could introduce a curvilinear coordinate system, alpha and beta, as we did in the plane strain case. Alpha parameterizes the curves with unit tangent t at every place. Beta parameterizes the curves with unit tangent s, the orthogonal trajectories of these trajectories here. Same notation as we did in plane strain. So this beta line, or beta curve, is the curve with unit tangent s. This says that theta has no derivative along such a curve. So d theta is 0 along the beta lines. Okay. So that means theta is only a function of alpha, some function of alpha, independent of beta. So that's then constant on a beta line in accordance with this restriction. If you remember from the plane strain discussion, those beta lines are satisfy the differential equation dx2 dx1 is minus cotangent of this angle theta. So the beta lines then are straight. This is at constant beta. This is now a function of alpha. We can integrate that and we get this equation. Okay, so you have a one parameter family of straight lines parameterized by the value of alpha. This equation is not so immediately useful, but this one is here. Remember how we defined t? That was the normalized gradient of w. So gradient w is its norm times t. This condition then, well, this immediately implies that s dot this gradient would be 0 because s dot t is 0. This again is the directional derivative along the beta line. That says that that's 0. So w is independent of beta. It's only a function of alpha. So it's constant again on a beta line. And that's the general velocity field that's consistent with with equilibrium in the anti-plane case. Let's do an example. And in the very last problem in your current homework, I'm asking you to generalize this example slightly. Okay. So let's look at a traction-free circular hole, similar to what we did in the plane strain case. Look at the material exterior to this hole of radius A. Let's use a polar coordinate system, r and phi. We have ER and E phi as we had before. So phi is the azimuthal angle, r is the radius, of course. Take the origin at the center of this hole. And the traction-free condition is this. Cauchy stress on n is 0, say at r equal a. And at that boundary is minus ER. Put in the expression for T, you get P times ER, because T is minus P identity. And then you get minus K, there was a, let's see. KT was the stress vector tau hat. So we get that dotted ER, and then there's another term which involves a tensor product with K, which when operating on ER is equal to 0. So you get scalar K, the yield stress and shear, the unit vector T dot ER along K, all this evaluated at R equal A. So P at R equal A, if there's no axial pressure gradient, then P is just a constant V. But since that has to vanish at R equals A, it's 0 everywhere because it's a constant. So in this case, there's no pressure field at all in the problem. And this equation then says T dot ER is 0 at R equals A, which means it has to be in the direction, because it's a plane vector lying in the plane, it has to be in the direction of E phi. So it's either plus E phi or minus E phi. In S, then, the orthogonal trajectory to T, if you pick T as plus E phi, then S is minus ER, and likewise, T equal minus E phi would imply S is plus ER. You have those two possibilities because of the choice of sign. Well, so this is true. We're seeking the vector field T in the material region exterior to the hole. T is purely azimuthal at the hole boundary, and it has to have 0 divergence in the material region. So I'm claiming that, in fact, T is E phi apart from sign in the material region as well. First of all, it's obvious this satisfies the boundary condition. It only remains to check the 0 divergence condition. So let's see if we have a solution or not. Well, I want divergence of T. As a preliminary step, I should compute the gradient of T and then take the trace to get the divergence. So with this proposed solution, grad T dx then would be plus or minus grad E phi dx, which is plus or minus d E phi by the chain rule. Let's see, what would this be? That would be E phi derivative with respect to phi, which is there a question? Okay, so d E phi would be the derivative of b phi with respect to phi. That's minus ER if you look back on the previous page, times d phi. So how are we going to get that? Let's see. As a side note here, if you write position in polar coordinates, that would be given this way. Z is x3. So dx, you just go through and use the product rule to take the derivative. Notice that r d phi, because ER, E phi, and K are orthogonal, r d phi is just E phi dot dx. So d phi, which I need here, is 1 over r E phi dot dx. And that gives me the 1 over r E phi dot dx with the sign, depending on how you chose T in the first place. So we immediately conclude that grad t is, apart from sine, is 1 over r tensor product d phi. The diff t then is the trace of that, which is identically 0, because that's er dot e phi, which is 0. So we indeed have the equilibrium condition satisfied in the absence of an axial pressure gradient. So the t lines, the alpha lines, are azimuthal, right? They're concentric circles. The t lines go around. So the alpha, you can take alpha to be phi, in fact, right? The curvilinear coordinate alpha can be identified with phi. And then beta is plus or minus r. Okay. Let's reconstruct the Cauchy stress. Minus p identity plus deviatoric part. No pressure here. We have this. We don't know t apart from sine. This tells us then the Cauchy stress has only one non-zero component on the polar basis here that we have. Just the phi z component of t is non-zero, and it's plus or minus the yield stress and shear. All other stresses are 0. Of course, t sub phi z is the same as t sub z phi from symmetry of t. We also had the velocity field consistent with this solution has 0 derivative along s. S, apart from sine, is er. So this er dot gradient w would just be the derivative of w with respect to r. So dw dr is 0. That's consistent with the conclusion that w only depends on alpha, which can be identified with phi. So if we go back here, w is only a function of phi, and its gradient then looks like this, and you can construct the d-tensor from this. This is as far as we can go without further conditions being imposed. So in your homework, the last problem, I'm asking you to generalize this problem slightly by allowing for an anti-plane shear traction on the boundary of the hole, where the intensity of that traction is less than the yield stress and shear, but we assume that the entire region exterior to the hole is yielded. Okay, and I'm hoping you can construct a velocity field consistent with that if you simply repeat this procedure that we have here, but a slightly more general result. Okay, so I'd like you to also construct the velocity field consistent with that boundary condition as posed in your homework. Okay, we'll come back to that anti-plane shear problem later after I talk about the small deformation theory. So we'll revisit the anti-plane shear solution we just had here by way of illustrating the small deformation theory, although that solution is valid for finite deformations. Okay. So the rigid plastic theory was motivated by the idea that if you have a finite deformation, and therefore a finite strain in general, then because the elastic strain is small in a metal, most of the strain must be due to plasticity. And so it makes sense to idealize that problem by taking the elastic strain to be negligible, so that H is essentially a rotation, producing 0 strain. Well, if that's not the case, right? If you don't have a large strain, if you have a small strain, then the elastic and plastic strains can be of comparable magnitude. So in that case, if you have a small deformation problem, which is quite often the case in engineering applications, then it would not make sense to neglect the elastic strain. So it's of some importance to establish a small deformation theory in which we account for the effects of both the elastic and plastic strain on an equal footing. We don't neglect one in favor of the other. So let's see if we can do that. Let's go back to basics and recall that our elastic deformation was the actual deformation gradient F times the inverse plastic deformation, or in other words, F is Hg, typically written Fe, Fp. And of course, G is K inverse. This is the plastic part of the deformation gradient. Well, based on this, we can construct an elastic strain tensor, as we have done already, and a plastic strain tensor, which we actually have not had occasion to do yet, and combine them into a total strain tensor. So the elastic strain, I'll append a subscript E because I intend to use E without a subscript for the total strain. That's a departure from what we've been doing before. So E sub E here will be the elastic strain. That's just, you take the Cauchy-Green deformation formed from the elastic part of the deformation gradient, subtract the identity. That's the usual definition of strain. Do the same for the plastic strain, G transpose G minus the identity. And I'd like to figure out how those figure in the overall strain, which is a half F transpose F minus the identity. So that's very straightforward. Right, F is Hg, then F transpose is G transpose H transpose, then we have an Hg minus the identity. Let's factor out a G transpose on the left and a G on the right. That gives us the first term. Then what I've done is subtract the G transpose G with the identity, so I better add it back in again. And then minus the identity is just the same as this last term here. So this we recognize as the plastic strain. This parenthesis with the half is the elastic strain, and so the total strain is given exactly by equation 1 here. The total strain is G transpose times the elastic times G plus the plastic strain. Okay. So you can think of the strain as a 6-dimensional vector, right? It's a strain belongs to the vector space of symmetric tensors, just like any other vector space. It's just twice as big as a conventional vector space. It's 6-dimensional. As in any vector space, we have something called the triangle inequality, and we also have, for example, the Cauchy-Schwarz inequality. In particular, the triangle inequality tells us the norm of a sum is bounded above by the sum of the norms. So we have the norm of the strain is bounded above by the sum of the norm of G transpose elastic strain G plus the norm of the plastic strain. Well, the norm of the elastic strain is always very small in practice for metal. So if G is of order 1 in magnitude, right? So for example, the case, no plastic strain would be G is orthogonal, right? And that's, an orthogonal tensor has a norm of, I think, square root of 3 or something like that. So if G is close, if the plastic strain is close to the identity, then G would certainly be order 1 in magnitude. And that's consistent with the smallness of the elastic or the plastic strain. So if the plastic strain is small, then G is certainly order 1 in magnitude. The elastic strain is small, so the overall strain will be small. Okay. So that small plastic strain combined with the physical requirement that the elastic strain be small, because of what we said earlier in the course, means that the overall strain is small. Right. So this, you can see here, neglecting the elastic strain makes sense if the strain is large, that effectively the plastic strain is large, even when the elastic strain is small in magnitude. Here we want to be in the regime where the overall strain is small, so the plastic strain should also be small. Okay, well, small strain is still possible even when the deformation is large. You could have a large rotation in the material, and the strain would still be close to zero. However, a small strain is implied by, say, smallness of the deformation gradient, the displacement gradient, I should say, not deformation gradient. We'll talk about the displacement gradient in a moment. So a situation in which your displacement gradients are very small would imply that the strain is small, but not vice versa, because you can have you can have a small strain with a finite displacement gradient due to finite rotation effects. So by the way, the regime of small displacement gradient is essentially the case studied in linear elasticity theory. So what we're aiming at here is a theory of elastic plastic response that's comparable to the classical linear theory of elasticity in the sense that the displacement gradients are everywhere small. So we'll consider in our further development here the case of small displacement gradients together with small plastic strain. By the way, this regime, we're gonna get an approximate theory here valid under these circumstances. That approximate theory is the cornerstone of virtually all solutions that are known in the theory of elastic plastic solids. Okay, and it's also of great practical importance because typically we design structures so that displacement gradients are under control. They're not large, because if they were, our structures would be very flexible. And for example, if you're designing a building or something like that, you want it to be stiff, and so the displacement gradients are typically small. Okay, before embarking on this discussion, we need to be a bit careful. The conventional definition of displacement gradient that you find in most treatises and books on continuum mechanics is slightly defective for reasons that we're going to talk about. So to set the stage here, let's go back to basic continuum mechanics and talk about regions in space and so on. Here's our reference configuration at time t. So we associate a material point with a location in some ambient space, call it E, or calligraphic E. And that space is called a point space. It's literally a space of points. And we can talk about the relative location of 2 points. So for example, a point at Y and a point at X, the location of Y relative to X, we call that Y minus X, the difference in these positions. Okay. That difference is actually a vector. So we would say that Y minus X belongs to not the point space, but rather the vector space associated with the point space. That's often called the translation space, or by which you should understand a vector space associated with this point space calligraphic E. The distinction is, is kind of a technical one, and people normally overlook it, but overlooking it can have some strange consequences that we don't want to fall into the trap of drawing inappropriate conclusions. So points themselves are not vectors, but relative position is a vector. Okay, so notice that the relative position does not rely on a choice of origin, right, relative to which you measure position. And in the definition of a vector space, there's no room for the concept of origin, in fact. So it's these translations from X to Y, the elements of which are actually vectors. We call them elements of the translation space. In the same way, we can associate the current configuration, material points in that configuration, with as elements of a point space, say, calligraphic E star. And the translations from one point to another Those are elements of a vector space, we'll call it E star, the translation space of calligraphic E star. So to emphasize the point here, I'm introducing a basis, capital EA, as we normally do, say in continuum mechanics, in elementary continuum mechanics, as a representative, say, Cartesian basis associated with the vector space E, and small ei as an example of a basis associated with the vector space E star. And it's useful, conceptually helpful, to distinguish E from E star. Right? For example, when we talk about two-point tensors like the deformation gradient is actually mapping the vector space E to the vector space E star. So when we say the deformation gradient has one leg in the reference configuration and one leg in the current configuration, mathematically what we mean is the deformation gradient operates on elements of E and produces elements of E star. It really has one leg in the vector space E and another leg in the vector space E star. So E and E star are background vector spaces, and the body resides in either E or E star, depending on whether you look at the reference or the current configurations. So this distinction between E and E star is completely consistent with the conventional interpretation of the deformation gradient, let's say, as a two-point tensor field. Okay, this is where conventional definitions of displacement encounter a difficulty. For example, in most of the literature, it's conventional to define a displacement as the difference between final position small x at time t and position capital X in the reference configuration. And small x is the value of the deformation function chi of x and t, and then we subtract capital X. Then we typically interpret, as shown in this diagram, x, let's say, as a position vector, that is, as an element of E, the vector space E. So in other words, it's the position of this point minus the position of this point, which we designate as the origin. Okay. So it's when we interpret x as a position vector, we're really treating it as the difference of two positions. This position here, where my cursor is, subtract this position here. And then we conventionally label this as the origin. When we do that, we then tacitly interpret capital X as a position vector. Likewise, small x is interpreted here in the same way as position vector. So the conventional definition entails the subtraction of a position vector, an element of E star, and a vector in E. But that's an undefined operation. In order to add and subtract vectors, both vectors must be elements of the same vector space. Otherwise, the operation makes absolutely no sense mathematically. Okay. So that's maybe well illustrated by using a Cartesian basis in both cases. For example, this is the position vector x. That's the difference between position x and position of the origin in the point space E star. Or because x is the value of chi, we could decompose chi in the same basis. We have these Cartesian components, chi sub I, ei. However, when we write x in this way as a position vector in E, which is the translation space of calligraphic E, the point space, we see that subtracting these two means we're subtracting elements of different vector spaces. It's not an allowed operation. It makes no sense mathematically. So we have to fix this in order to properly define the displacement. And that's a prerequisite setting up a theory for small displacement gradients. We had better get the displacement right, a consistent definition of displacement, before we then work with displacement gradients. So again, I want to emphasize this is, as it stands, this operation is mathematically forbidden because vector addition and subtraction is only defined for elements of a given vector space. You can't, so this operation is subtracting apples and oranges, essentially, right? You're subtracting two quantities that live in different spaces. Not allowed, not a defined operation. To fix this, we introduced the notion of something called a shifter. A shifter acts to take a given vector from an element of one vector space and simply embed it in the other vector space without changing its magnitude or orientation. It just inserts a vector from one vector space into another vector space. We call that a shifter. And this notion of shifter, by the way, you can find it in the older literature. In particular, that paper Zach gave us by Doyle and Erickson. You will find a really extensive discussion of the notion of shifter, which I'm endeavoring to simplify here. The notion of shifter fell out of favor when people stopped using index notation and started using boldface notation. And that led to certain inconsistencies, as it turns out. So in the later literature after Doyle and Erickson, for example, in Truesdell and Knoll's very famous treatise on continuum mechanics, and the subsequent textbook and monograph literatures, which were based largely on Truesdell and Knoll, they completely omitted the notion of shifter. And this led to some fairly serious misconceptions. Among them, the idea that linear elasticity is not a frame invariant theory. And that's actually based on a misconception that can be traced to the omission of the essential notion of shifter. Okay. And by the way, going down the page here, you can find a good discussion of the notion of shifter in this book by Marsden and Hughes, a very famous book, Mathematical Foundations of Elasticity. It's in Dover, so it's very inexpensive. And now it's on B courses, thanks again to Zach. The relevant pages are 57 to 61. So this is a synopsis of that discussion. So what we're going to do is take our position vector x, which is an element of E, and shift it to become an element of E star, which is the same vector space that x belongs to. So we'll operate on x with something called a shifter. I'll call it 1, because it's sort of related to the notion of an identity, but not quite. It's an identity that takes a vector in one vector space and simply makes it into an element of another vector space without changing it, if you can visualize what I'm talking about. We transport the vector parallel to itself without changing its magnitude from E to E star. So we don't change the vector, we change the vector space in which it lives. Okay. So the 1 here is intended to remind you of the identity, but it's not quite. Identity maps a vector space to itself. This shifter is a kind of an identity, but it maps one vector space to another vector space without altering the vector. So I'll write it as 1x, and 1x we'll call it x star. And now we define the displacement this way. Mathematically, that makes sense because we're subtracting two elements of the same vector space, E star. So this x star lives now in E star. And this will be our modified definition of the displacement. Okay. So this definition makes sense, as we've indicated. And it also implies that this object 1, it's a map of vectors into vectors, so we identify it as a tensor. It maps E to E star, so it's a 2-point tensor just like F. Okay. So for example, using Cartesians, we'd write x as cap xa EA. The tensor operating on that, tensor on a vector is a linear operation, so you can take the components out in front, and you get 1 on EA, we'll call it EA star. And EA star is an element of E star. It's the same, essentially the same vector as EA, E1, let's say. It's just that it now lives in the vector space E star instead of E. Now, you're thinking, I'm sure, that this is all a lot of nonsense, because if we're not changing the vector, then what's the point? Well, you'll see later the point is an essential one when we talk about things like invariance under superposed rigid motions. Under superposed rigid motions, x doesn't change, but it turns out x star will change. And that's what saves the day in linear elasticity theory, and implies that linear elasticity is actually a frame invariant theory, unlike the claims made in much of the literature. I'll come back to that notion. Okay, so let's, for example, continue with Cartesians. We can write U. We're now subtracting. The definition of U means we're subtracting elements of E star. And the small ei we introduced as a basis for that vector space E star. So we can write U as a linear combination of the elements of that basis in the usual way. And the UI then will just be the projections of U onto the basis elements. It's EI dot x minus x star. This makes sense because EI and x star are both elements of the same vector space, so we can do the dot product. Okay. So not only are sums and differences only defined for elements of the same vector space, but also, in fact, dot products have a similar requirement. It only makes sense to take the dot product of two vectors if they belong to the same vector space. So EI dot x is our usual Cartesian small xi. EI dot x star would be EI dot xa E star A. So here's the xa. EI dot EA star, I'll call it delta IA. And that's, of course, EA star is 1 EA. This then tells us how to reconstruct the tensor 1, this shifter, because now we know its components in the mixed basis, EI, EA. This is how we would construct a tensor from its components in a mixed basis, just like the deformation gradient. So this would be our delta IA, EI, EA. Now, a word of caution here. The delta IAs, these are, I'm using delta like the Kronecker delta, but it's not quite the same. If you should happen to choose a basis EA, say E1, which is aligned with little e1, E2, capital E2 aligned with little e2, cap E3 aligned with little e3, then the shifted versions would have also the same alignments, and these dot products would just be ones or zeros like the Kronecker delta. So you could get confused very easily by thinking the delta IA must be the Kronecker delta, but there's no such requirement because the EA stars do not have to have the same orientation as the small e's. So in that case, these would be dot products of unit vectors. They would be direction cosines of one basis relative to the other. Okay, and a matrix of direction cosines, if you may recall, is always an orthogonal matrix. We'll elaborate on that in a moment. So this is not the Kronecker delta. It doesn't have to be. Much of the confusion in the literature occurs because people have identified delta IA with the Kronecker delta, which is not required. It's conceptually important to not make that special case, not make that special choice, with the capital E's being aligned with the small e's, right? It's important to allow distinct bases, just to keep things just to keep track of the distinct behavior of this one versus the identity. Okay. So as I mentioned, the salient property of the shifter is that it transports vectors in E into E star without changing them. It doesn't change their magnitudes or directions. So we say a parallel transports these vectors from one vector space to the other. So for example, suppose you have two vectors in E, the referential vector space, v1, v2, and they're shifted versions, in small v2. And I'm using small v instead of capital V because being elements of a different vector space, they're conceptually distinct from the capital V's. Okay, so we should use a notation that maintains that distinction. Okay, so the idea that we don't change, that the shifter simply parallel transports the capital V's into the small v's without changing their orientation or length means that the dot product of the small v's is the same as the dot product of the capital V's. This dot occurring in the vector space E star and this dot occurring in the vector space E. Well, V1, of course, is the shifter times capital V1, etc. So we have this. And so we have the conclusion that the one preserves the dot product, right? The shifter doesn't alter the dot product between the two vectors. And that's basically the definition of an orthogonal tensor, if you remember from continuum mechanics. So we conclude immediately that the shifter is orthogonal, just like the conventional identity is orthogonal, but it's a distinct mathematical concept. Okay, so from this equation, let's work on it a bit. By using the definition of transpose, we can write the left-hand side as V1 dot 1 transpose 1 V2. And this has to be true for any pair of vectors V1, V2 in the vector space E. And that means 1 transpose 1 is the conventional identity, capital I. I'll write that as the identity on the vector space E. Right? Because you could choose, for example, V1 and V2 to be the elements of an orthonormal basis, capital E1, 2, and 3, right? And then you would conclude that this equation would boil down to this one. Right? So in Cartesians, this equation we've just deduced reads this: delta IA, delta IB is the conventional Kronecker delta, capital A, capital B. Right? So this is ones and zeros, the identity matrix. But because of the capital AB notation here will identify that as the referential identity that's consistent with the fact that this identity holds for vectors in E, so 1 transpose 1 must be the identity on that vector space. Well, you can likewise solve these for capital V in terms of the small v's. 1 inverse now is 1 transpose because of the orthogonality. And then look at the dot product of small v1 with small v2. That's again cap v1 dot cap v2 because of the defining property of the shifter. That's 1 transpose small v1 dot 1 transpose small v2. Use the definition of transpose again, you get this. This has to be true for all pairs of small v1 and v2 now in the vector space E star, which means 1, 1 transpose must be the identity for the vector space E star. But because I went to the trouble of distinguishing the vector space E star from the vector space E, I'll also distinguish the identity in that vector space from the identity in this vector space. I'll call it small I instead of capital I. In Cartesians, this equation would read, if you decompose this use the basis representation of 1 that we indicated, 2-point representation, this equation would have this component form. Delta IA delta JA, sum on A, is Kronecker delta IJ. So you can compare that expression with this one. Okay? And this makes, either one of these, again, makes clear that this delta IA are the elements of an orthogonal tensor. Beyond that, say, because the EA star are the parallel transports of the EA, if we pick these to be some fixed associated with a given Cartesian system in the point space calligraphic, or in the vector space E, and these are the parallel transports of these fixed vectors, these vectors are fixed in the vector space E star. So these dot products will just be numbers, right? This is some fixed basis in E star, this is another fixed basis in E star. So these are just constants. If you reconstruct the shifter tensor from its components, you have constants here. These are constant basis elements. So this is a uniform tensor. It's independent of position in either of the point spaces. Okay? And we'll make use of that property. By the way, you'll find a nice discussion of this also in the Doyle-Erickson paper. Although it's an old paper, it's it's a very fundamental piece of work, and it's worth a read. Something to notice: you can write 1. You can pre-multiply by the identity in the vector space E star, because 1 has a 1 foot in that vector space, right? So pre-multiplication by the identity in that vector space, the first factor of 1 lives in that same vector space, so this doesn't change anything. So you can write 1 as the spatial identity. I'll call that the spatial identity, small I, associated with the vector space E star. You can write 1 as the spatial identity times 1. The spatial identity, on the other hand, is 1 transpose. And if we group terms here, 1 transpose 1 is the referential identity. So we can conclude that the spatial identity on 1, multiplying 1, is the same as 1 times the referential identity. And you can believe that because the component form of this equation would be delta ij delta ja equals delta ib delta ba, where the delta ij is the conventional Kronecker delta. Sum on j, you get delta ia. Here, delta BA is the conventional Kronecker delta. Sum on B, you get delta IA. So this is obviously true. Okay. So this is, you can think of this as the relationship between the shifter tensor and either the referential or the spatial identities. And again, these things, it's important to maintain these conceptual distinctions, especially when we talk about important concepts like frame invariance. By the way, this is a fairly crude way to prove that the shifter is a uniform tensor. Here we had resorted to a particular coordinate system to prove that. Another way to prove that uniformity is to note that this defining relationship of x star means that the shifter, is the gradient of x star with respect to x. In other words, 1 is the referential gradient of x star. In books in continuum mechanics, for example, Gerton's book, you can see a nice proof that if you have an orthogonal tensor, which is a gradient of something, then that orthogonal tensor must be uniform. And that's effectively identical to the proof that you've seen in continuum mechanics that a rotation accompanying a rigid body motion is necessarily uniformly distributed. Right? So that's, maybe a more sophisticated demonstration that the shifter is uniform. So that's important. So we have our displacement finally defined here in a mathematically consistent way. X star is shifted version of x. We can use the chain rule to compute the referential displacement gradient. I'll use capital G for the referential gradient, capital grad U. Operating on dx is du by the chain rule. That's d chi, which you remember is f dx, minus d1x, but 1 is uniform, so that that's the same as 1 dx. Factor that out like so. And this purports to be true for all d capital X, therefore the parentheses are the same, so you get the deformation gradient is the shifter plus the referential displacement gradient. In most of the literature, you will find this written as the identity plus the referential displacement gradient. This is where everything starts, this is where we first encounter the trouble. The shifter is not the referential identity or even the spatial identity. It's distinct. Right? So this incorrect expression in parenthesis typically uses the basis of linear elasticity, and it leads you to the incorrect conclusion that linear elasticity is defective on the grounds that it's not frame invariant. Untrue. If you decompose this in Cartesians using the basis capital EA for the vector space E and the basis small ei for the vector space E star, then in Cartesians you simply get this formula. And the referential gradient of U simply has components ui comma a. That's partial ui with respect to capital XA. Okay, so now that we've sorted out what we mean by a displacement gradient, we can eventually now talk about a theory for small displacement gradients. Let's have a look at the strain displacement relation. Preliminary to that, we need the right Cauchy-Green deformation, F transpose F. Use this expression. We have this, and multiply through the terms. One of those terms is going to be 1 transpose 1, which we've seen as the referential identity. Then we have these cross terms, 1 transpose grad U transpose 1, grad U transpose grad U. Subtract the referential identity and put a half in front, and we get the Lagrange strain. The Lagrange strain is then given in this form in terms of the referential displacement gradient. By the way, you see this expression makes sense. F is a 2-point tensor. 1 we've seen as a 2-point tensor. Referential gradient of U, that would be ui comma a ei tensor product ea, that's also a 2-point tensor. So we're adding objects of the same type. This would be wrong. This is I is a purely referential tensor, whereas grad U, if we can't subtract it from F to get grad U because this is a 2-point tensor. Subtracting a referential tensor makes no sense mathematically. Tensor addition, subtraction, and so on, you have to add objects of the same type. Okay, so this is the consistent strain displacement relationship. In most of the literature based on this incorrect formula. In other words, in most of the literature, people simply interpret this shifter as the conventional identity. If you do that, you get this incorrect strain displacement relationship, which you often find in the literature. Okay. If you use Cartesians, then this expression here in Cartesian simply becomes this, and you can see the explicit role played by the shifter. As you can see, it's necessary to make sense of the index structure, right? When you sum on I here, you get something with an AB subscript. You have to have, each term has to have only an AB free indices A and B. And you get that here when you sum on I with the shifter, you sum on I again with the shifter, and you sum on I here, you get something with free indices A and B. So the shifter, although it seems like a, something we can safely ignore. In fact, it's not the case. Let's have a look at superposed rigid body motions. In such a motion, position in the current configuration goes to a new position, which is the rotated version of the original position plus a shift, C of t. So Q here is a rotation tensor. And you know that taking the gradient of this with respect to capital X gives you F plus is QF. Everybody's seen that before. Q is a spatial rotation tensor. It maps, it rotates the vector space E star, in effect. And you can see that as follows. Let's write X as a position vector in E star using the Cartesian basis small ei, and define ei plus to be QEI. So if we write Q is Q times the spatial identity, and then write the spatial identity as EI tensor product EI, then we can conclude that Q is EI plus tensor product EI. So if EI is a right-handed orthonormal basis, then EI plus is another right-handed orthonormal basis, the rotated version of the original. So then X plus, small x plus, is XI, put X here, that's XI QEI plus C of t. QEI is EI plus C of t. We can write C, we can decompose it in the basis EI plus, write the components as CI, right? With EI plus is only a function of time because of Q. So the CIs, because C is only a function of time, CI will only be a function of time also. So you can write X plus as XI plus CI EI plus, which gives us a basis decomposition of X plus. Components X plus I are just given by these parentheses, right? So we could write the Cartesian components are just, the components are not rotated, but they're shifted by C. And since the components are the values of the deformation function components, we have chi I plus is chi I plus Ci of t. Take the partial of this equation with respect to capital XA, you get F plus IA, the components of the deformation gradient, equal simply to FIA, d chi I d capital XA, and then these have no capital X derivatives. So in this interpretation, the components of F don't change under superposed rigid motion. Of course, F itself does because of the Q factor. Right, F is Q times this basis decomposition. The components come out in front, and then you have Q up multiplying these tensor products. That's the same as the tensor product of QEI with capital EA. QEI is EI plus, okay? If you plug in the formula we had for F in terms of the shifter and the displacement gradient, components, plug it into this formula, you get F plus is grad U plus the plus version of the shifter, where we have the same EI plus in each case. So these are this is Q grad U, and the shifter after a superposed rigid motion is Q times its original value. So you see, the shifter, unlike the conventional identity, the shifter changes. And that change is essential to restoring the frame invariance of linear elasticity, for example. More importantly, you see that the relationship between the deformation gradient and the displacement gradient is preserved under a superposed rigid body motion. In other words, if F was grad U plus the shifter before the superposed rigid motion, then it's also true after the superposed rigid motion. And that's because the original equation with the shifter is a genuine tensor equation because it involves the addition of objects of the same type, 2-point tensors, okay? If you instead use this incorrect relation where you replace the shifter by the conventional identity, as is often done, then you would not get this nice equation. The reason being, F plus is QF, but I plus is I. because the vector space E is not being rotated. Okay, so this equation would be destroyed by a superposed rigid motion. And that would lead you to conclude, what must grad U be after superposed rigid body motion in order to preserve the notion that F plus is QF, and it gives you a complicated formula. But it didn't make sense in the first place, and it's just an inspection of this formula indicates that it can't be right, because grad U then would be the difference between a two-point tensor and a purely referential tensor, and there's no such thing. You're not allowed to make that subtraction. Okay, I think I'm taking too long on this subject. Okay, so notice also from what we've just done, the use of a shifter allows you to interpret a superposed rigid motion as a rotation of the background vector space E star, because we rotated EI to EI plus, which is now a basis for the rotated version of this vector space. So we can think of a superposed rigid motion as not so much a rotation of the body itself, but a rotation of the background vector space. And that's really more in keeping with the interpretation of frame invariance as invariance under observer transformations. For example, as an observer looking at, if you change your orientation relative to a body in space, from your point of view, you're carrying your vector space with you, like say, the frame set by your, if you're wearing some glasses, you have a frame of reference associated with the fixed axes in your glasses, let's say. When you change your orientation relative to the body, it's your vector space is being rotated relative to the body. So that's more in keeping with the notion of frame invariance as invariance under observer transformations, which I think is the more fundamental way of viewing frame invariance. Okay, so we've deduced along the road here that grad U plus is Q grad U. Let's see what this implies for U plus itself. Well, using the chain rule, du plus would be grad U plus dx. X, the original X in the vector space E has not changed, right? But then grad U plus is Q grad U dx, that's Q du, but Q is spatially uniform, so we can sneak it inside this derivative, the derivative with respect to position, right? And then integrate du plus is dqu, just integrate that immediately. You get u plus is qu plus some vector function of time alone, which means, this part means that u is a genuine spatial vector with a possible shift. This d of t could be a shift, okay? And that's exactly physically how you would think of it. For example, suppose you imagine drawing a displacement vector in a body, or in a, think of a displacement vector as a directed arrow, right, with a certain length and orientation. If you're flying past in an airplane, let's say, all the while observing that displacement vector, from your point of view, that displacement vector appears not only to shift location in space, according to d of t, but also to rotate, change its orientation in space, okay? So as you're flying past in an airplane, it appears to you that the displacement is truly a spatial vector combined with a shift, d of t. That would not be the case if you use the traditional definition of a displacement vector, because x doesn't change, whereas little x goes to q little x plus c of t. And so you would not get this interpretation of the displacement. Although, this thought experiment about flying past in an airplane certainly, I think, substantiates and reinforces this result here, underlined result. Okay, let's go back to the strain displacement relation. we all know that the strain should be insensitive to superposed rigid motions. Let's make sure that it is. After superposed rotation, E plus would be the same as E, except everything would have a plus appended to it. Every variable would have a plus sign on it now. 1 plus is Q1, and take the transpose of that, you get this. Q is the spatial rotation. Q transpose Q is the spatial identity. Then we have grad U. And this is a 2-point tensor, the first factor of which lives in the vector space E star. So the pre-multiplication by the spatial identity doesn't change it. You get 1 transpose grad U. Similarly for the other terms, you get here spatial identity on 1 is simply 1. We get what we had before, and then this gives spatial identity. This times grad U is grad U itself, and we get the original E as required. Okay? So this is consistent with our common notion that the strain is insensitive to rotations, superposed rotations. By the way, I made a big point of using convective coordinates earlier in the course. Let's see how that would work. So remember, in convective coordinates, if you look back in your notes, we had this basis representation where GI was the reciprocal basis associated with the curvilinear coordinate system, and the components were just the difference in the metric, this metric in the current configuration minus the initial metric with a half in front. And these were the metrics induced by the convective coordinates. We're not changing the coordinates, remember, in this formalism. And the way you compute the small g's is by taking small gi dot small gj, and small gi was small x comma I, etc. Small x is now the displacement plus this shifted x, x star. So we do that here twice. The shifted x, we need a comma I for that. That's 1x comma I. 1 is spatially uniform, so that's 1x comma I. Capital X comma I was GI, if you recall. So we get 1 GI, which we'll call it GI star. So this shifts the GI into an element of the vector space E star, call it GI star. It's the same vector, just now interpreted as an element of the vector space E star instead of E. In fact, we can write 1 then as 1 times the referential identity. The referential identity, if you go back to your notes, is cap GI, tensor product, cap G super I. 1 on GI is GI star, so you can write the shifter in this form right here. Notice that the metric G star induced by the GI stars, given by the dot products here, is 1 GI dot 1 GI, 1 being orthogonal preserves the dot products. You just get the conventional referential metric. This is invertible, so the inverse would be G star super ij would be the same as G super ij. And then the reciprocal basis, you'd raise the index in the usual way. You get this, G star is 1G, so you get 1 times the conventional, the reciprocal basis elements we had before. We can compute connection coefficients, which would be Christoffel symbols here in our Euclidean space, in the usual way by taking these dot products. 1 again is spatially uniform, so it comes out of the partial derivative. And 1 preserves dot products because it's orthogonal, so we just get the referential connection coefficients as we had before. Now we want our displacement, remember, to be a spatial vector, so it should be an element of E star. So we can decompose it in this way. We can decompose it in, say, for example, the dual basis G star super K, because these live in E star. And then take, let's see, to get the metric here, we need to take a comma I and a comma J and so on. Take the comma I in the usual way, we get connection coefficients by taking the derivatives of these. The connection coefficients are the same as the gamma bars that we had before. And this parenthesis we called UK stroke I earlier on. And then we have the G star reciprocal basis. Now we take the dot products as indicated to get the small GIJs. Here we get the G star IJ, which is the original metric GIJ. And when you make these dot products, you're going to get G star super K, G star sub J is the Kronecker delta, the actual Kronecker delta, conventional one, ones and zeros. You sum on, let's see, you're going to get delta super K sub J, you're going to get a U sub J comma I, for example. And then another one here, you're going to get this, and then here you're going to get these you can write this way. So this last expression is what your book that discusses convective coordinates. This is the correct mathematically meaningful strain displacement relation in convective coordinates. Okay, in which you interpret the components as being insensitive to superposed rigid motions. It's just the basis that gets rotated such that Q becomes a spatial vector. Okay. Okay, we're over time, so now we're ready to actually talk about small displacement gradients, now that we know what a displacement gradient really is. So if there are no questions, I'll see you next time. But, please go ahead and ask a question if you have one at this stage. Okay, so this notion of shifter, go ahead and read the relevant pages in Marsden and Hughes now that you have that on B courses. Thanks again, Zach. And as I say, it's an older concept. When people were being very careful about tensor analysis in the old days, they used index notation. Then the notion of shifter was entirely natural. It's in later times when people started to throw out index notation because it's cumbersome and started using boldface notation instead. That's where the confusion sneaked in, where people started thinking, well, the tensor is just a bold-faced object, an object in boldface, and that's the end of it. You still have to respect the rules of the game, which are that you cannot add tensors of different types, right? Or subtract different tensors of different types. It's not a meaningful operation. So that there's a good discussion in Marsden and Hughes. Maybe a simpler and more clearer one in Doyle and Erickson, and I'm just trying to give you the benefit of that somewhat lost subjects in the intervening years, but which is essential to a proper formulation of the small displacement gradient theory. Okay, and the reason is, let me spend another moment of your time here. Classical linear elasticity is for small displacement gradients. Not having the correct definition of the deformation gradient with the shifter leads you to a conclusion that linear elasticity is not frame invariant. A theory that's not frame invariant is trash. It's complete garbage. The reason being, let's say you design a building on the basis of linear elasticity, which people do every day. You design a building at, you give the design based on your analysis, 4 o'clock, it's the end of the day. You give it to your boss in San Francisco at 4 o'clock. At 5 o'clock, the analysis will be invalid because of the rotation of the Earth between 4 and 5. And so that would really be a bizarre situation, right? If linear elasticity were not frame invariant, then almost all engineering analysis, which is conducted on the basis of linear elasticity, might be valid at 4 o'clock, but then be invalid at 4:01, and even more invalid at 5, and so on. So, this is just silliness. There's nothing wrong with linear elasticity. If it's done right, it's perfectly frame invariant. Okay, thank you for listening to all that propaganda, and I'll see you next time.